Out beyond Earth's orbit, distance stops feeling like kilometers and starts feeling like years in a single human lifetime. Space can carry a traveler past the moon, toward Mars, and through the patient work of machines out to the cold edge of the solar system where interstellar space begins. Tonight, this calm journey follows the true limits of time, speed, and survival, and shows how far one life can realistically go. Before settling in, please like the video, subscribe to the channel, and let the quiet scale of space guide the night gently forward. The Milky Way provides the widest practical map for thinking about how far a single human lifetime can reach. It is a galaxy of immense size, a rotating system of stars, gas, dust, and dark matter whose bright disk spans roughly 100,000 light-years across its faint outer extent. Within that disk, the Sun and its planets occupy a small region, one address among hundreds of billions of stars. The galaxy is large enough that most of it remains distant even in imagination. Yet it is also close enough to be mapped in structure and in scale. For a lifetime question, the Milky Way is the first outer frame that is both meaningful and limiting. A light year is a distance, defined by how far light travels in 1 year through vacuum. This unit is used because ordinary length units become unwieldy beyond the solar system. It has a quiet implication built into its name. Even the fastest messenger in nature takes years to cross distances between stars. The Milky Way's diameter in light years therefore carries a time meaning as well as a spatial meaning, even before any spacecraft is considered. A journey that spans thousands of light years does not only span space, it spans thousands of years for light and far longer for anything that carries mass. Inside the Milky Way, most stars are separated by several light years in the Sun's region, while in denser regions the spacing can be smaller. A single light year is already an interstellar distance. It is larger than the solar system's main planetary region by a wide margin. Yet a single light year is also small compared with the distance to most stars in the galaxy. It is not the distance to the galactic center. It does not reach the opposite side of the disk. It is only a first unit in the ladder that connects local space to the larger galactic map. The nearest stars to the Sun lie a few light years away. This is the first rung that matters for travel in a lifetime because it defines the nearest possible stellar destinations. The galaxy contains many closer and farther systems, but the nearest ones set the minimum interstellar crossing. Beyond those nearest stars, the neighborhood thickens into a local region where hundreds of star systems lie within a few tens of light years. Beyond that, the galaxy becomes a tapestry of spiral arms, star-forming regions, and old stellar populations spread across thousands of light years. Each step outward multiplies the distance and therefore multiplies the time required for travel under the same speed. The Milky Way's internal geography is layered. The disk is a thin, rotating plane where most stars reside. Within it, spiral arms mark regions with more gas and more recent star formation. The central bulge and bar hold higher stellar density near the center. The halo extends above and below the disk, with older stars and globular clusters on wide orbits. Beyond the bright disk lies a large dark matter halo, an invisible mass structure inferred from how stars and satellite galaxies move. For scale, the main point is that the Milky Way is not a small neighborhood. It is a vast gravitational domain where distances between major features are measured in thousands of light years. A lifetime question naturally invites a distance ladder, a sequence of thresholds from far to near. At the far end of the ladder lies the full diameter of the galaxy, a span so large that even light requires about 100,000 years to cross it. No human lifetime approaches that duration. Even a journey across a small fraction of the galaxy is still a journey across thousands of light years, a timescale far beyond individual experience. This establishes the first calm boundary. A human lifetime does not reach across the Milky Way in any literal travel sense under known physics. The galaxy is the outer frame that revealed what is permanently out of reach for a single human lifespan. The next rung inward is the distance from the Sun to the galactic centre, measured in tens of thousands of light years. The galactic centre is a region of dense stars, gas, and a supermassive black hole. It is a real place in the Milky Way structure. Yet it is so distant that reaching it within a lifetime is beyond any realistic technology. In a lifetime framing, the galactic centre remains not a destination but a coordinate, a point that defines where the Sun sits and how far inward the Sun lies from the centre of the disk. The same is true of other large galactic landmarks, such as the far side of the disk or the outer halo. They define a map, not a reachable itinerary. Within that map, the nearer rung is the local arm environment where the Sun resides. The Sun lies within the disk, not at the centre, and it orbits the galaxy on a timescale measured in hundreds of millions of years. This orbit is slow compared with human life, yet fast compared with the motions of continents on Earth. The Sun's motion places the solar system within a broader flow through the galaxy, but it does not change the travel question in a lifetime, because the Sun's orbital motion is not a vehicle that can be directed. It is a background drift that affects the solar system's location over geological time rather than over a single life. The ladder then moves inward to the nearer star systems. These are measured in a few light years, not thousands. They're still far. Light takes years to cross the gap. A spacecraft travelling at present-day deep space speeds would take many thousands of years to reach even the nearest star. Yet in the ladder of size, this is the first zone where the number is small enough to hold in the mind without dissolving into pure abstraction. A few light years is a distance that can be spoken as a single phrase and still be understood. It is the first boundary that separates a lifetime of travel within a star system from a lifetime of travel between stars. The next inward rung is the scale of the solar system itself. Planetary orbits are measured in astronomical units rather than in light years, and the outer planets lie tens of astronomical units from the Sun. Beyond them, the Kuiper belt and scattered disk extend farther. Beyond them lies the heliosphere, the bubble of solar wind influence, and beyond that the local interstellar medium resumes. Even when these outer boundaries are included, the solar system remains a small region compared with the distance to the nearest stars. This is why the ladder begins with the Milky Way and then drops quickly to nearby stars. The solar system is a local island. The nearest star is a separate island. The space between them is large enough that, in practice, it separates the era of planetary travel from the era of interstellar travel. This distance ladder serves a calm purpose. It defines the reachable domain before any propulsion or biology is discussed. The far rungs are impossible within one lifetime because they require travel times far beyond the span of decades. The near rungs are possible in principle because they belong to the solar system, where travel times range from days to years and, for the farthest human-made probes, decades. Between these two lies a boundary that is neither philosophical nor emotional. It is the interstellar gap, measured in light years, where even the nearest destination requires years of light travel time and, for ordinary spacecraft, millennia. The ladder also implies a second kind of smallness. In a galaxy of 100,000 light-years across, a region a few tens of light-years wide is tiny, yet that region can still contain hundreds of stars. The Milky Way is vast, but it is also sparse. Stars are separated by large gaps. Most of the galaxy's volume is not filled with matter. It is filled with thin gas and dust, radiation and magnetic fields. This sparsity is part of why the ladder is steep. A traveller does not move through crowded material. A traveller moves through emptiness measured in light years. The primary obstacle is distance itself. This first section therefore establishes the widest frame for the title, One Lifetime in Space. How far could you go? The answer will not be found at the scale of the whole galaxy, because a lifetime is too short. The answer will be found on the inner rungs, where the solar system and the nearest interstellar distances define the practical horizon. The ladder now stands in place the Milky Way as the unreachable outer map, the galactic centre and major structures as distant coordinates, the nearest stars as the first true interstellar step, and the solar system as the small island where real travel has already occurred. With this outer frame set, the path inward can now turn to the rule that governs every rung, the speed of light and the limits it imposes on travel and communication. Light sets the pace of the universe because it is the fastest way that information can move through space under modern physics. It is not simply fast in a practical sense. It is a limit woven into the structure of space and time. In a lifetime question, this limit becomes the first hard boundary because it sets the minimum possible travel time for any signal and the unattainable ceiling for any object that carries mass. A human lifetime is measured in decades. Interstellar distances are measured in light years. These two measures meet at the speed of light, where the meaning of far becomes a matter of time as much as a matter of space. A light year is a distance defined by the path light travels in 1 year. By definition, light crosses 1 light year in 1 year. This is already a calm revelation of scale. The nearest stars are several light years away, so even light needs several years to reach them. A signal sent across interstellar space cannot arrive sooner than the number of light years separating the source and the destination. This delay is not an engineering problem, it is a physical fact. It means the communication with a spacecraft far from Earth becomes slower in the most literal sense, and it means that coordination across star systems cannot be instantaneous, no matter how advanced the technology becomes. The speed of light is constant in vacuum. This constancy does not match ordinary intuition formed from slow human experience, where speeds appear to add and subtract simply. In modern physics, the constancy of light speed leads to a new relationship between distance and time for moving observers. This relationship is described by relativity. In relativity, the speed of light remains the same for observers moving steadily relative to each other, and space and time measurements adjust in a consistent way to preserve that fact. The constancy has been supported by many kinds of experiments and by the broad success of technologies that rely on relativistic corrections, such as satellite navigation and precision timing. The key consequence for travel remains simple. Nothing that carries mass reaches the speed of light. The reason lies in energy. To accelerate an object, energy must be supplied. As the object's speed increases toward the speed of light, the energy required for additional increases rises steeply. The object does not merely need more fuel in a linear way. It requires a rapidly increasing amount of energy for smaller and smaller gains in speed as it approaches the limit. In the framework of relativity, reaching the speed of light would require infinite energy for an object with mass, which makes it unattainable. This does not prevent very fast travel. It defines a ceiling that cannot be crossed. This ceiling also shapes the meaning of one lifetime. If a person lives for several decades, then any journey measured in light years becomes immediately constrained. Even if a spacecraft could travel at a large fraction of light speed, the travel time in the departure frame remains at least the number of light years divided by that fraction. A spacecraft travelling at 1/10 of the speed of light would take about 10 years to cross 1 light year in the simplest constant speed picture. At 1/100th of the speed of light, it would take about 100 years. Real missions take longer because they must accelerate and often must decelerate. These numbers illustrate the basic slope. Reaching beyond the solar system within a lifetime requires speeds that are far beyond those of present spacecraft. Communication shares the same limit. A message sent to a probe 1 light year away arrives 1 year later at the earliest. A reply arrives 1 year after that. This creates a natural lag of years even at modest interstellar distances. For a lifetime, this means that direct conversation with a spacecraft beyond a few light years becomes slow in an unavoidable way. Commands and responses cannot form a quick loop. The craft must operate with autonomy, making decisions locally based on its sensors and its mission goals. Even at the far edge of the solar system, communication delays become noticeable. Across interstellar distances, delay becomes the dominant feature of control. The limit also separates travel from observation. Astronomy observes distant objects by receiving their light. This means that distant space is always seen in the past. A star 10 light years away is seen as it was 10 years ago. A galaxy 1,000,000 light years away is seen as it was 1,000,000 years ago. The universe is therefore a layered record of past states. For travel within a lifetime, this creates a quiet contrast. Observation can reach far because light travels freely and quickly by cosmic standards. Travel cannot reach as far because objects with mass cannot keep up. Relativity introduces another feature that is sometimes misunderstood as a way around the lifetime limit. Time dilation causes a fast-moving clock to tick more slowly, compared with a clock at rest in the departure frame. A traveller moving near light speed experiences less time than the people who remain behind. In the traveller's frame, the distance in the direction of travel is also reduced by length contraction. Together, these effects can make a long journey feel shorter to the traveller if the speed is extremely high. Yet the effects do not allow the traveller to arrive sooner than light in the departure frame. They do not allow a signal to arrive sooner than the light travel time. They change the amount of time experienced by the traveller, not the outside time measured by those who remain near the origin. In a lifetime question, time dilation matters only if the spacecraft reaches speeds very close to the speed of light. At present technological levels, spacecraft speeds are far too low for time dilation to make a meaningful difference. Even in a hypothetical advanced future, time dilation would be bought with enormous energy costs and with increased hazards from dust and gas impacts in interstellar space. High speed reduces travel time but increases the energy of collisions with tiny particles. This creates a physical trade. Fast travel becomes both energetically expensive and more dangerous to the vehicle. The speed limit is therefore not only a theoretical boundary, it is a practical guide that shapes which speeds are sensible. The speed of light also protects a consistent order of cause and effect. If information could travel faster than light, then different observers could disagree about the order of events in ways that undermine causality. Relativity preserves causality by making light speed the maximum speed for information transfer. This is one reason the limit is treated as a deep principle rather than a technical detail. It underlies the consistency of the universe's behavior across space and time. Within the solar system, the speed of light still matters, but it often feels small because distances are measured in light minutes and light hours. Signals to Mars can take minutes. Signals to the outer planets can take hours. These delays matter for mission operations, but they remain manageable in human time. At interstellar scale, delays move into years. This shift changes the entire style of exploration. A craft beyond the solar system cannot be treated as a remote-controlled vehicle in the ordinary sense. It must be treated as an independent agent operating far from its creators, with communication that arrives slowly and with decisions that must often be made without immediate guidance. The speed limit also clarifies what one lifetime in space can mean. A lifetime cannot reach distant stars unless the travel speed becomes a significant fraction of light speed. If a person's lifetime is used as the time budget, then the maximum reachable distance in light years is roughly the fraction of light speed achieved times the number of years available, adjusted downward for acceleration, braking, and mission overhead. With present spacecraft speeds, that distance remains far below 1 light year. With hypothetical advanced speeds, it could reach fractions of a light year or more, but only for small craft and with large energy investment. This framing remains calm because it does not depend on speculative physics. It depends on measured constants and on the structure of relativity. Light crosses interstellar distances with ease because it is light. Mass cannot do the same. Communication inherits the same rule. A lifetime is therefore a strict limiter not because the universe is hostile, but because the universe is large and because its deepest speed is finite. With the rule of light speed established, the inward path can move from the abstract limit to the practical environment that any traveller faces. The interstellar medium is thin, yet at high speeds it becomes a source of impacts and radiation. It shapes how close a real craft can approach the speed limit while still surviving. In a lifetime question, survivability becomes part of reach, because speed and endurance are linked to the physical conditions between stars. Between stars, the space a traveller crosses is not a perfect vacuum. It contains a thin mixture of gas, dust, magnetic fields, and energetic particles. This mixture is called the interstellar medium. In ordinary human life, the interstellar medium has no direct presence. It cannot be felt and it cannot be seen without instruments. Yet over the long distances relevant to a lifetime in space, it becomes part of the environment that defined what travel speeds are practical. The medium is sparse, but it fills the gaps between stars, and at high speed even sparse material matters. Most of the interstellar medium is hydrogen, with helium as the second most common component. Hydrogen can be neutral, meaning its electron remains bound, or ionized, meaning it has lost its electron and exists as a plasma. In some regions, hydrogen can form molecules, creating cold molecular clouds that later collapse to form new stars. In the local region of the Milky Way around the Sun, the medium tends to be relatively low density compared with these dense clouds. It is still not empty. It contains atoms and ions moving with thermal speeds and bulk flows shaped by the galaxy's motions and by past events such as supernova explosions. Dust is a smaller component by mass, but it is important for both astronomy and travel. Interstellar dust grains are tiny solid particles, often made of silicates, carbon-rich compounds, and, in colder regions, ice coatings. Dust absorbs and scatters starlight, producing dimming and reddening along long sight lines. It also re-radiates absorbed energy at infrared wavelengths. Dust outlines the structure of the Milky Way in dark lanes where it blocks background starlight. In travel, dust becomes a hazard because a grain striking a fast-moving craft carries kinetic energy that can damage surfaces. The hazard grows quickly with speed. Kinetic energy increases with the square of speed. At the slow speeds of most present spacecraft, dust impacts are a manageable risk treated with shielding and careful design. At speeds required for interstellar travel within a lifetime, which would likely be a significant fraction of the speed of light, dust impacts become much more severe. Even tiny grains can act like microscopic projectiles. A single impact can produce a local burst of heat and a spray of material. Repeated impacts can erode surfaces and damage instruments. For light sail concepts, where large thin surfaces are used to gain speed, dust impacts become especially significant because thin materials can be punctured or weakened over long distances. Interstellar gas also matters at high speed. Individual atoms are tiny, but at very high relative velocity they deliver energy when they collide with a craft's leading surface. At near relativistic speeds, collisions with hydrogen atoms can contribute to heating and to material damage. They can also produce secondary radiation through interactions that generate energetic particles. The interstellar medium therefore becomes not only a source of mechanical erosion, but also a contributor to radiation exposure when speed is high. At lower speeds, the effect remains small. At higher speeds, it becomes part of the design problem. Magnetic fields thread through the interstellar medium. They are weak compared with laboratory magnets, yet they extend across large volumes and influence the motion of charged particles. Cosmic rays, which are high-energy particles arriving from distant sources, travel through this magnetized environment. The cosmic ray background is a steady radiation field in interstellar space. It includes protons and heavier nuclei at high energies. These particles can penetrate spacecraft materials and can damage electronics and biological tissue. The interstellar medium therefore includes both the material that can strike a craft and the radiation that can pass through it. For a lifetime journey, radiation exposure is a constant constraint. A crewed craft would need shielding to reduce health risk, which increases mass and reduces achievable speed. A robotic craft can be hardened and can tolerate some damage through redundancy, but long exposure still increases the chance of failure. The trade remains calm and structural. Higher speed reduces time exposed to cosmic rays, but it increases dust and gas impact energy. Lower speed reduces impact energy, but it increases time exposed to radiation and increases the duration over which systems must remain reliable. The interstellar medium therefore turns the lifetime question into a balance between speed and endurance. The interstellar medium is also not uniform. Density varies by region. Some lines of sight pass through denser clouds or through regions of higher dust content. Some pass through lower density cavities. The Sun itself moves through the galaxy and passes through different environments over millions of years. A spacecraft on a specific path would also pass through particular local conditions. Route choice could reduce risk by avoiding known dense regions, but the distribution of small dust grains and the fine structure of the medium are not fully mapped at the detail that would matter for extreme speed travel. Uncertainty therefore remains even with careful planning. The medium also affects communication subtly. Radio signals can pass through interstellar space, but the medium can cause dispersion and scattering, especially at certain frequencies and along certain directions. These effects can be corrected in many cases with signal processing and by choosing suitable frequencies, but they add complexity. Over a lifetime mission that reaches far from Earth, communication becomes a problem of both distance and weak signal strength. The medium does not block communication in most cases, but it becomes one more layer in a system already dominated by the inverse square dimming of signal power with distance. Navigation is another interaction with the medium. A craft traveling for decades must maintain orientation and course. It can use star trackers, gyroscopes, and timing systems. It can use pulsars, rapidly rotating neutron stars that emit regular signals, as natural beacons. The interstellar medium does not provide landmarks. It is too thin and too diffuse. Navigation is therefore an act of measurement against distant references, maintained over long time. Small deviations early can become large offsets later. Correction maneuvers consume energy and propellant, and they require a craft to remain functional and autonomous. In the context of a lifetime, the interstellar medium also sets a quiet practical limit on the speed that can be chosen for crewed travel, even if propulsion could reach high fractions of the speed of light. The shielding required to protect humans from impacts and radiation would likely be heavy. Heavy shielding increases mass, and increased mass demands greater energy to accelerate, which may not be available. This tends to push the most plausible lifetime interstellar concepts toward robotic probes rather than crewed craft. A small probe can accept a higher speed and a higher risk. A human habitat cannot. The medium thus shapes not only engineering but also the likely order of exploration. The interstellar medium also provides a reminder of what space is made of. It is the thin residue of stellar evolution, enriched by supernovae and winds. It contains the material that becomes future stars and planets. In that sense, the space between stars is not a void without history. It is the galaxy's shared environment, where matter cycles through different phases. Yet for travel, the key property remains its thinness. It is thin enough that a spacecraft can cross it without being slowed by drag in the ordinary sense, but it is dense enough that it becomes dangerous at high speed and influential over long duration. For the title One Lifetime in Space, how far could you go? This environment sets the stage for the time budget. The maximum distance reachable in a lifetime depends on speed. Speed is constrained by the speed limit of light and by propulsion capability. Propulsion capability is constrained by energy and mass. Energy and mass are constrained by the need for shielding and by the need for reliable systems that survive the medium. The interstellar medium therefore turns the question into a coupled problem. A lifetime is short, a light year is long. The medium makes very high speed expensive in protection. The medium makes low speed expensive in endurance. The answer will come from the balance that is most realistic for humans and for machines. And that balance begins with turning a lifetime into a time budget for distance. The next inward step therefore moves from environment to time. It defines a realistic span for a human lifetime and translates that span into reachable distances under different speed assumptions, without promising technologies that do not yet exist. In that translation, the lifetime horizon becomes a clear boundary shaped by physics rather than by wish. A lifetime is not a single fixed number, yet it can be treated as a practical time budget for travel. Human lifespans vary, and not every year of a life can be devoted to flight. Childhood, training, preparation, and recovery all belong to the same arc. Even if a person could depart at adulthood and remain in motion until old age, the available travel time is still measured in decades, not centuries. This simple fact sets a quiet boundary before propulsion is considered. The question of how far one lifetime can go becomes, first, a question of how much time can be spent in transit. A calm approach begins with a generous window. A long adult life might allow several decades of travel time. This does not require an exact figure to be useful. The key point is that the available span is far smaller than the timescales of most cosmic motion, and far smaller than the light travel times associated with most interstellar distances. When time is measured in decades, and distance is measured in light years, the conversion depends on speed as a fraction of the speed of light. If a spacecraft could travel at the speed of light, then each year of travel time would cover 1 light year by definition. A lifetime of several decades would then cover several decades of light travel distance. This is a simple upper bound, and it is unattainable for any craft with mass. It is useful because it shows the best possible case for signals and the absolute ceiling for motion. No realistic travel plan exceeds it. Every realistic travel plan falls below it, often far below. The next step is to consider fractions of the speed of light. If a craft travels at 1/10 of the speed of light, then it covers 1/10 of a light year per year of travel time in the departure frame. Over 1 decade, it covers about 1 light year. Over several decades, it covers several light years. If a craft travels at 1/100th of the speed of light, then it covers 1/100th of a light year per year. Over 1 decade, it covers about 1/10 of a light year. Over several decades, it covers a few tenths of a light year. These conversions are calm arithmetic, but their meaning is large. They show that interstellar reach within a lifetime requires speeds far beyond those achieved by present spacecraft, which travel at tiny fractions of the speed of light. The time budget must also include acceleration and deceleration. A craft does not begin at full cruise speed. It must speed up, and if it intends to stop or slow near the end, it must slow down. If the craft uses a short, powerful push and then coasts, the acceleration phase may be brief compared with the cruise phase, but it still reduces average speed. If the craft uses long, gentle acceleration, average speed may be much lower than peak speed for much of the journey. In a lifetime budget, this matters because decades are not long enough to hide long acceleration phases. A mission that spends many years accelerating and many years braking can reduce the distance covered compared with a mission that reaches cruise speed quickly and coasts for most of the time. The practical result is that the distance reachable in a lifetime is determined by average speed, not peak speed. Average speed is the total distance divided by total travel time. It includes the slow beginning, the long middle, and the approach. If a craft reaches 1/10 of the speed of light only briefly and spends most of its time at much lower speed, its average may be only a small fraction of 1/10. The lifetime distance would then be reduced accordingly. This is why time budgets must be treated as full mission budgets rather than as simple cruise estimates. A lifetime budget also includes the time required for meaningful arrival. If the mission goal is to visit a destination and return information, then travel time is not only the time spent moving, it is also the time spent operating at the destination. If the craft is crewed, time at the destination may be essential for exploration and survival. If the craft is robotic, it may need time for observation and for transmitting data back. Transmission from great distance is slow not only because of light travel time, but also because power and antenna limitations can require long communication sessions. A craft that reaches the outer solar system may spend years sending its results. A craft that reaches interstellar space may need long intervals for transmission. These operational times compete with travel time inside a lifetime budget. Relativity introduces a subtle modification to the time budget. At high speeds, time dilation reduces the time experienced by the traveler. A traveler near the speed of light experiences less time between departure and arrival than an observer at rest in the departure frame. This could, in principle, allow a traveler to cross larger distances within a single experienced lifetime, if the craft could reach and sustain extreme speed. However, this benefit is limited by energy cost and by hazard. Time dilation becomes large only very close to the speed of light. In that regime, kinetic energy becomes enormous and dust and gas impacts become more energetic. A lifetime budget for a crewed craft must include the protection required to survive. Protection increases mass. Increased mass makes reaching those speeds harder. The practical effect is that time dilation is unlikely to extend human reach within one lifetime, unless technology reaches a level far beyond current capability. Within nearer-term realism, time dilation remains a small correction rather than a decisive advantage. Even without time dilation, the time budget yields clear categories of reach. Within the solar system, decades are enough to cross from the inner planets to the outer regions with present methods, though not quickly and not with ease. Missions already show that robotic craft can operate for decades and travel to the outer planets and beyond. A human lifetime can therefore include travel to the Moon, to Mars, and potentially to farther destinations within the solar system if life support and radiation protection are managed well. The solar system is large, but it is still measured in light hours rather than light years across its main planetary domain. Beyond the solar system, the time budget becomes severe. The nearest stars are several light years away. Even at 1/10 of the speed of light, reaching them would take several decades in the departure frame, before accounting for acceleration and braking. This begins to approach the full span of an adult lifetime. At 1/100th of the speed of light, reaching even 1 light year would take a century, which exceeds the travel time available for one person. This shows a quiet threshold. For interstellar travel within a single lifetime, average speeds must likely be closer to 1/10 of the speed of light than to 1/100th, and the mission must probably be designed as a flyby or as a one-way journey with no expectation of return within the same life. The time budget also clarifies what remains out of reach even in generous scenarios. The Milky Way's main structures are thousands of light-years away from the Sun. Even a craft travelling at 1/10 of the speed of light would require tens of thousands of years to cross tens of thousands of light-years. Time dilation would not change the outside universe's timeline, and it would require extreme speed to change the traveller's experience time significantly. The practical result remains. One lifetime does not reach the galactic centre or the far side of the disk. The lifetime budget, therefore, is a narrowing funnel. The outer universe is unreachable by travel and reachable only by observation. The galaxy's major landmarks are unreachable by travel and reachable only as coordinates. The nearest stars become the first possible interstellar targets, but only if speed is raised by orders of magnitude beyond current spacecraft. The solar system becomes the most realistic domain for significant travel within one human life, especially for crewed missions. Robotic missions can extend farther in time, but they do not carry the limitation of biology. This section's work is to hold the time budget steady without forcing it into a single number. Decades are the scale of a life. Light years are the scale of interstellar distance. Fractions of light speed convert one into the other, and average speed, not peak speed, sets the outcome. Acceleration and braking reduce average speed. Operations and communication consume time. Protection and reliability impose mass and energy costs that shape feasible speed. Within these constraints, the lifetime horizon becomes clear. It reaches deep into the solar system, and it approaches the nearest interstellar space only if speed becomes far higher than present practice. With time converted into distance in this calm way, the inward path can now ground the discussion in real motion. The next step turns from abstract fractions of light speed to the actual speeds and durations achieved by human missions. From low Earth orbit to the fastest deep space probes, those baselines will show what is already reachable within a lifetime today, and how far the present limits remain from the first light-year distances. Real spaceflight provides the most grounded measure of how far a lifetime can go. It replaces abstract speed fractions with actual mission profiles, actual propulsion methods, and actual years spent travelling. The record is modest compared with the scale of the solar system, yet it is also remarkable in context. Human beings have reached orbit, walked on the Moon, lived for months and more than a year in microgravity, and sent robotic craft to every major planet. A lifetime in space, measured by human time, has already extended beyond the Earth-Moon system through robotic explorers and has begun to touch the boundary between the solar system and interstellar space through a handful of long-lived probes. The baseline begins near Earth. Low Earth orbit is a region where spacecraft circle the planet in roughly 90 minutes. Speeds in low Earth orbit are high, measured in kilometers per second. Yet they are high only because Earth's gravity is strong and because orbit is a state of continuous free fall. These speeds are impressive in human terms and form the first rung of space travel. They also show how small Earth is in the solar system, because an orbital craft can circle the planet many times in a single day. In a lifetime scale, low Earth orbit is close and accessible. It is a space environment, yet it is still within the shelter of Earth's magnetic field and within reach of rapid rescue and resupply. The next baseline is the Moon. The Moon lies a few light seconds away and a few days away by spacecraft travel using chemical propulsion. Human missions reach the Moon in less than a week, and robotic missions do so regularly. In a lifetime budget, the Moon is close. It is a destination that can be reached, explored, and returned from within a small fraction of a life. It is also a place where the reality of space becomes clearer. No atmosphere, harsh temperature swings, and radiation exposure higher than on Earth. Even at this short distance, the environment becomes more demanding, and life depends on technology. Mars is the next major benchmark. Mars is not a fixed distance. Its distance from Earth varies as the planets orbit the Sun. Travel time depends on trajectories that balance fuel and time, often using transfer orbits that take months. Mars missions therefore operate on a scale of months for transit rather than days. This remains within a lifetime comfortably, yet it begins to introduce the idea of long-duration isolation, delayed communication, and the need for reliable life support. For robotic missions, Mars has been reached many times. For a crewed mission, it remains a future challenge, but its travel time is still on the scale of a year for a round-trip mission concept depending on alignment and stay duration. In the lifetime frame, Mars is reachable, but it is not trivial. Beyond Mars lie the outer planets. Robotic missions reach them in years. Jupiter is reached in several years by many trajectories, often assisted by gravity flybys. Saturn is reached in longer spans, sometimes close to a decade depending on the path. Uranus and Neptune are reached by flyby missions on timescales longer still. These missions demonstrate that a lifetime can include robotic travel to the outer solar system, with time to spare for long observation. They also show that, for humans, the time is not the only constraint. Radiation, life support, and the mass of supplies become limiting factors. Robotic missions can accept years of travel because they do not need air, water, or food. Their constraints are power supply, reliability, and thermal management. The fastest deep space probes provide another baseline. Their speeds are achieved through strong launch energy and through gravity assist from planets. Gravity assist allow a spacecraft to exchange energy with a planet's orbital motion, changing the spacecraft's speed relative to the Sun. This technique has been used repeatedly to extend mission reach. Even so, the resulting speeds remain tiny compared with the speed of light. They are excellent for crossing the solar system, but they do not shrink the interstellar gap into a lifetime scale. The Voyager missions provide the clearest lifetime scale benchmark for reaching beyond the main planetary system. They launch in the late 20th century and travel past the giant planets using a favorable alignment. They continue outward for decades, operating far from the Sun and crossing into the outer heliosphere. Their longevity shows that machines can survive for long periods in deep space. Their speed shows the limit of current methods for reaching interstellar distances. Even after decades, the Voyagers travel only a tiny fraction of a light year. Their distance from the Sun is measured in light hours, not light days, and far less in light years. This is a calm, essential scale comparison. A lifetime of travel at Voyager-like speed reaches the outskirts of the solar system and begins to enter interstellar space. It does not reach another star. Another baseline comes from New Horizons, a mission designed for a fast passage to Pluto and beyond. Its speed after launch and gravity assist is high by solar system standards. It reaches Pluto in less than a decade and continues outward into the Kuiper Belt. This shows that with careful planning, a robotic mission can reach the outermost known planetary region within a small fraction of a human life. It also shows that even fast solar system travel remains confined to a region that is tiny compared with a light year. There are also missions that achieve high speeds near the Sun, such as those that use close solar approaches to gain velocity. The fastest speeds achieved by any human-made object occur near close passes to the Sun, where gravity accelerates a craft. These peak speeds are impressive, yet they are not sustained. They occur in a specific orbital geometry and do not represent a constant cruise speed toward interstellar space. This distinction matters for lifetime reach. Peak speed does not determine distance covered over decades. Sustained outward velocity and long-term mission endurance determine it. Human time in space provides a different baseline. Individual astronauts spend months and sometimes more than a year in orbit. This is long enough to reveal the physiological effects of microgravity and the psychological demands of confinement. Yet it is still close to Earth and supported by resupplier medical systems. The longest continuous human missions remain far shorter than the travel times required for outer planet journeys, let alone interstellar journeys. This suggests a practical boundary. While robotic craft can take years to reach Jupiter or Saturn, crewed craft must contend with biology that becomes harder to support as duration increases and as distance makes resupply impossible. Within a lifetime, the real reach of human presence is therefore limited to near-Earth space and the Moon at present, with Mars as a plausible extension under future development. The real reach of robotic craft extends to the outer planets, the Kuiper Belt, and the heliosphere. The reach of communications extends much farther, because radio signals travel at the speed of light and can cross interstellar distances, though their strength diminishes with distance and their round-trip delays grow into years. These baselines show what a lifetime can already touch. It can touch orbit quickly. It can touch the Moon easily. It can touch Mars in months. It can touch the outer planets by robot in years. It can touch the Kuiper Belt in a decade. It can touch the heliosphere boundary over decades. It can touch interstellar space just beyond that boundary in a longer span. Yet it cannot touch the nearest star in any literal travel sense with present speeds. This establishes a calm gap. The lifetime horizon within present technology is the outer solar system and the heliosphere for robots, and nearer destinations for humans. To go farther within one lifetime, propulsion must change, not only in power, but in efficiency and in how propellant is used. Chemical rockets provide high thrust but low exhaust speed. Electric propulsion can provide high efficiency but low thrust. Nuclear systems can provide long-lived power and potentially higher performance. Gravity assist can add speed without fuel, but only within a planetary system. These are the tools that shape the next inward layers of the question. The next step, therefore, moves from baselines to boundaries. Chemical propulsion has limits that appear as mass and fuel constraints. Those limits define how far a crewed craft can realistically go within a lifetime without requiring propulsion beyond current practice. With the real baselines held in mind, the inward path can now examine why chemical rockets, despite their usefulness, cannot carry a lifetime traveler very far beyond the solar system's inner regions without becoming impractical. Chemical propulsion is the foundation of human spaceflight because it delivers high thrust and dependable performance. It lifts payloads from Earth, places crews into orbit, and sends probes toward other worlds. It does this by releasing energy stored in chemical bonds and expelling hot exhaust at high speed. The reaction pushes the spacecraft forward. This method is powerful in the near term, but it is limited by physics that becomes unavoidable when distances and timescales expand. For a lifetime question, chemical propulsion sets a clear boundary. It can take a traveler to nearby destinations and return them. It cannot make the solar system small, and it cannot make interstellar space reachable within a human life. A rocket must carry its reaction mass. It carries fuel and oxidizer, tanks and engines, and all the structure required to hold and feed propellant. To gain speed, it must throw mass backward. The faster the desired speed change, the more mass must be thrown away as exhaust. The achievable change in velocity depends on exhaust speed and on the ratio between the rocket's initial mass and its final mass. Chemical exhaust speeds are limited by the temperatures and molecular weights of combustion products. Even at high performance, chemical exhaust remains far below the speeds needed for interstellar travel within a lifetime. This means that to gain large velocity changes with chemical engines, the rocket must carry extremely large propellant fractions. The mass ratio grows quickly, and practical designs run out of possibilities. Staging helps within the solar system by shedding empty tanks and engines, reducing the mass that must continue accelerating. Staging enables launches and makes deep space missions possible. Yet staging does not remove the underlying exponential growth of required propellant as desired speed increases. It delays the wall. It does not move it far enough to make light-year travel a lifetime-scale project. For interplanetary travel, chemical propulsion works because the needed changes in velocity are measured in kilometers per second. For interstellar travel within a lifetime, the needed changes in velocity would need to be far larger, reaching thousands of kilometers per second and beyond. Chemical rockets cannot provide this for meaningful payloads without propellant masses that become unmanageable. Even within the solar system, chemical propulsion is most useful for the short, powerful phases of a mission. It launches from Earth, performs major burns, and then often yields to coasting and to gravity assists. Long continuous chemical thrust is rare because it consumes propellant quickly. The lifetime reach of chemical propulsion is therefore strongly tied to launch energy and to trajectory design. It can send a craft toward Mars efficiently. It can send a craft to the outer planets when paired with gravity assists. It can deliver a crew to the moon and back. It becomes increasingly difficult to use it for round trips beyond Mars without enormous mass and complex logistics. For crewed missions, the chemical boundary is tighter because life support adds mass. A crewed spacecraft must carry shielding, supplies, habitats, and redundancy. Every added kilogram must be accelerated. Chemical propulsion must therefore lift not only the crew, but also their environment. This is why crewed missions to Mars remain challenging, even though robotic missions reach Mars routinely. The travel time is manageable in a lifetime. The mass and reliability requirements are the difficult part. Chemical propulsion can deliver the required velocity changes for Mars missions, but doing so with safe margins and with robust life support requires large launch capacity and complex staging. Chemical propulsion also faces storage limits that matter more as mission duration grows. Some high-performance chemical propellants are cryogenic, meaning they must be kept very cold. Over months or years, managing boil-off becomes difficult. Insulation helps but adds mass. Refrigeration requires power. In deep space, thermal conditions can be cold, yet solar heating and internal heat still matter. Long-term storage of large quantities of cryogenic propellant adds complexity. Storable propellants exist, but they often offer lower performance and involve toxic handling. For a lifetime traveler, the demand would be for long-duration reliability and safety, and chemical propellant storage becomes one more risk factor. The chemical boundary also includes braking. To return from a destination or to enter orbit around a planet, a craft must slow down. Braking requires additional propellant or careful use of atmospheres for aerobraking. Aerobraking can reduce fuel needs by using atmospheric drag, but it requires precise control and a suitable atmosphere. It also imposes heat and stress on the vehicle. For Mars, aerobraking and aerocapture are conceptually useful, but they add design demands. For outer planets, atmospheres exist, but the challenges of entry are extreme. For small bodies without atmospheres, braking requires propellant. Every kilogram of braking propellant must be accelerated on the way out, compounding the mass challenge. Within a lifetime, chemical propulsion therefore tends to favor a certain set of reachable domains. It supports repeated travel to low Earth orbit and back. It supports missions to the Moon and, in principle, to nearby asteroids. It supports missions to Mars with careful planning and large launch capacity. It supports robotic missions far beyond. But crewed missions become increasingly difficult as distance grows because resupply becomes impossible and the mass of safety systems rises. Chemical propulsion can place a human traveler on a trajectory to the outer solar system, but sustaining life for the required years and returning within a lifetime becomes a different order of problem. The propulsion is not the only limit. It is one part of a larger system. The calm conclusion is that chemical propulsion defines a lifetime horizon that lies inside the solar system's inner and middle regions for crewed travel. It can reach farther with robots because robots tolerate long travel times and do not require a habitat. For a human traveler, a lifetime is too short and the biology too demanding to make chemical travel to the outer solar system routine. The distance can be crossed, but the cost, mass, and time become extreme. For interstellar space, chemical propulsion is not merely difficult, it is practically irrelevant. It cannot raise speed by orders of magnitude without propellant masses that overwhelm any craft design. This boundary does not end the story. It points toward propulsion methods that use propellant more efficiently or that rely on external energy. Electric propulsion can provide high exhaust speeds with low thrust, useful for long-term robotic missions and possibly for cargo transport. Nuclear systems can provide power for electric propulsion and possibly higher performance engines. Gravity assists can amplify launch energy without fuel. These methods do not erase distance, but they alter what a lifetime budget can accomplish. The next inward step therefore moves from chemical limits to the practical role of electric propulsion and nuclear power systems, clarifying what they can extend within a lifetime and where their own limits appear. Electric propulsion changes how a spacecraft uses propellant. Instead of releasing energy through chemical bonds to heat exhaust, an electric thruster uses electrical power to accelerate propellant ions to very high speeds. The thrust produced is small, but the efficiency in terms of propellant use can be far higher than chemical rockets. This makes electric propulsion valuable for long-duration missions, especially robotic missions that can accept slow acceleration over months and years. In the context of one lifetime in space, electric propulsion and nuclear power systems extend reach not by making the solar system small, but by making certain long journeys more practical and by reducing the propellant mass required for a given change in velocity. An ion engine is a common example. It uses electric fields to accelerate ions, often from a noble gas propellant, expelling them as a beam. The exhaust speed is high, which means each kilogram of propellant produces a larger change in velocity than in a chemical engine. The trade is thrust. Ion engines push gently. A spacecraft with an ion engine can accelerate continuously for long periods, gradually building speed over months. The accumulated velocity change can become substantial. This style of propulsion is well suited to missions that do not need quick bursts of speed but benefit from steady, efficient acceleration. Electric propulsion depends on power. The energy to accelerate ions must come from solar panels or from a nuclear power source. Near the Sun, solar power is abundant enough for many missions. Farther out, sunlight weakens rapidly, beyond the orbit of Mars, and especially beyond the orbit of Jupiter. Solar power becomes less effective unless panels become very large. Large panels add mass and area, which can complicate spacecraft design. This is why many deep outer solar system missions rely on radioisotope systems rather than on large solar arrays. Radioisotope power supplies provide steady heat that is converted to electricity, and they can operate for decades. They provide modest power, not the high power needed for extremely strong electric propulsion, but they are reliable and long-lived. Nuclear electric propulsion is a concept that combines a fission reactor with electric thrusters. A reactor can provide higher power than radioisotope systems. With higher power, electric thrusters can produce more thrust, though still small compared with chemical rockets. A nuclear electric system could, in principle, accelerate a spacecraft continuously over long time and reach higher speeds than solar electric systems could at great distance from the Sun. Such systems face engineering challenges: reactor mass, shielding, heat rejection, and long-duration reliability. Heat must be radiated away, requiring radiators that add mass. Shielding must protect sensitive electronics and, if the mission is crewed, protect the crew. These requirements set practical limits on how large and powerful a reactor can be for a spacecraft. Within a lifetime frame, electric propulsion is most clearly useful for robotic exploration and for cargo. It can move payloads efficiently between planets. It can spiral out from Earth orbit without the need for large chemical burns. It can adjust trajectories gradually and deliver high total changes in velocity for modest propellant mass. These strengths align with missions where time is available. A cargo system can take a few years to reach Mars if it saves mass and cost. A robotic probe can take several years to reach the outer planets if it gains flexibility and efficiency. The lifetime question is not only about the traveler, it is also about the machinery and infrastructure that supports travel. Electric propulsion can move supplies and build capability ahead of crewed missions, expanding what a lifetime traveler can do by improving logistics even if it does not carry the person the whole way. For a crewed mission, electric propulsion is limited by thrust. A crewed ship needs not only efficient use of propellant, but also time constraints and radiation constraints. Long spirals outward from Earth and long transit times increase exposure to radiation and increase demands on life support. Chemical propulsion provides fast departure burns that shorten time in transit to inner destinations. Electric propulsion provides efficient long burns that can reduce propellant mass, but often at the cost of longer travel time. This suggests a division of roles. Electric propulsion may be best for cargo, for robotic precursors, and for deep space maneuvering, while chemical propulsion remains important for quick departures and for high-thrust maneuvers, at least within current and near-term technology. Radioisotope power and nuclear reactors also shape the outer limit of lifetime robotic reach. A probe with a long-lived power source can continue operating as it travels outward. It can maintain communication, perform course corrections, and run instruments for decades. This is why missions like Voyager and others can continue sending data from far distances. The power available is small, yet it is steady. With careful energy management, a spacecraft can remain functional for a long time. This long durability is part of how a lifetime in space can extend beyond the outer planets in robotic form, even if crewed travel remains confined. For reaching interstellar distances within a lifetime, electric propulsion is not a direct solution. Its thrust is too low to accelerate a craft to the high fractions of light speed required for light-year travel in decades. Even if a reactor could supply large power, the mass of the system and the efficiency limits would keep speeds far below the needed scale. Electric propulsion can help a probe leave the solar system more efficiently than a purely ballistic trajectory, and over long time it can build significant velocity change, but it remains a method for tens of kilometers per second and perhaps beyond, not for thousands of kilometers per second. This means its role in the lifetime question is mainly to extend reach within the solar system and to improve the efficiency of exploration, not to open the nearest stars. Even within the solar system, the difference between tens of kilometers per second and the thousands of kilometers per second implied by interstellar travel is vast. A craft traveling at tens of kilometers per second requires thousands of years to cross 1 light year. A craft traveling at 1/100th of the speed of light, which is about 3,000 kilometers per second, would cross 1 light year in about 100 years. Electric propulsion does not approach this regime in practical designs. This is not a dismissal, it is a scale statement. Electric propulsion is a powerful tool for solar system exploration. It is not a bridge to the nearest star within a single lifetime. The lifetime horizon nevertheless benefits from electric systems in a quiet way. They make deep missions more capable. They allow more maneuvering far from the sun. They allow flexible trajectories that can visit multiple targets. They allow long-duration station keeping and precise orbital insertion without large chemical propellant loads. For a lifetime traveler, these capabilities could support missions to Mars and beyond by building infrastructure, delivering supplies, and enabling better staging points. They also enable scientific exploration of the outer system within a human lifetime through robotic proxies, extending what a human civilization can learn and touch during 1 generation. With electric and nuclear power systems understood as practical tools within the solar system, the next inward step returns to another method of gaining speed, without fuel gravity assists and close sun maneuvers. These are techniques that use the geometry and gravity of the solar system itself to increase velocity. They do not violate the speed limit of light. They do not create new energy from nothing. They exchange momentum with planets and exploit the sun's deep gravitational well. In a lifetime question, they define how fast a craft can leave the solar system and how far a lifetime can extend toward its outer boundary. Within the solar system, speed can be increased without carrying extra fuel by borrowing energy from motion that already exists. Planets orbit the sun with enormous momentum. The sun's gravity forms a deep well where speeds naturally rise as a spacecraft falls inward. A spacecraft can use these features through carefully planned trajectories. Two techniques stand out as quiet workhorses of deep space travel gravity assists and close sun maneuvers that concentrate a propulsive burn where orbital speed is highest. Together, they show how far geometry can extend reach within a lifetime, while also revealing the limits of what geometry alone can do. A gravity assist is an encounter with a planet that changes a spacecraft's velocity relative to the sun. The planet's gravity bends the spacecraft's path, In the planet's own frame, the spacecraft arrives and departs with nearly the same speed, ignoring small effects. In the sun's frame, however, the planet is moving, and the spacecraft can leave with a different velocity than it arrived with. The spacecraft gains or loses energy relative to the sun by exchanging a tiny amount of orbital energy with the planet. The planet's motion barely changes because the planet is so massive. The spacecraft's motion can change noticeably because the spacecraft is small. This is not a trick. It is an exchange within conservation laws. Gravity assists have been used to reach the outer planets and beyond. A spacecraft can visit Venus, Earth, and Jupiter in sequence, using each encounter to reshape its trajectory and adjust its speed. The technique can also be used to slow a spacecraft relative to the sun by taking energy away, which is useful for missions that need to approach the sun closely or enter certain kinds of orbits. In a lifetime reach context, the main value of gravity assists is that they increase heliocentric speed without adding propellant mass. They allow a spacecraft to leave the inner solar system faster than a direct chemical burn would allow for the same launch mass. The gain from a gravity assist depends on geometry. The spacecraft must pass through the planet's moving gravitational field in a way that changes its direction appropriately. The maximum speed change is limited by the planet's orbital speed and by how close the spacecraft can pass safely. The encounter distance is constrained by the planet's atmosphere, radiation belts, moons, and hazard environment. A close pass may allow a larger deflection and therefore a larger change, but it also increases risk and can impose thermal and radiation constraints. A more distant pass is safer, but yields less effect. Mission designers choose paths that balance these constraints. Gravity assists also depend on timing. Planets must be in the right places at the right times. A mission that uses multiple assists often requires years of travel within the inner solar system before the final departure toward the outer system is achieved. This time cost matters in a lifetime budget. Gravity assists can raise eventual speed, but they may consume a portion of the lifetime in the process. For robotic missions, this can be acceptable. For crewed missions, long looping trajectories increase time in deep space and increase radiation exposure. This is one reason why high-thrust departures remain attractive for crewed travel to nearer destinations, while gravity assists remain most valuable for robotic probes and cargo. A close sun maneuver changes the picture by using the sun's gravity to raise speed where it matters most. As a spacecraft falls toward the sun, it accelerates. Near perihelion, the point of closest approach, the spacecraft's speed relative to the sun can become extremely high. If the spacecraft performs a propulsive burn at this point, the burn produces a larger change in the spacecraft's orbital energy than the same burn would produce far from the sun. This is because adding speed when speed is already high changes energy more strongly. This effect is often called the Oberth effect. It is not a separate force. It is a property of orbital energy and how it depends on velocity. The Oberth effect can be used with chemical propulsion or other propulsion types. The key requirement is that the craft must reach a close sun trajectory, which itself can require careful planning and, often, gravity assists from inner planets to lower perihelion safely. The closer the perihelion, the stronger the effect, but the harsher the thermal environment. Near the sun, sunlight is intense, and a spacecraft must carry heat shields and protective design to survive. These shields add mass. Mass reduces acceleration capability and can limit overall performance. The craft must also remain stable and control its orientation under extreme heating. These constraints define a practical lower limit on how close the craft can safely pass, and therefore define the usable strength of the maneuver. The value of a close sunburn is most evident for missions aiming to leave the solar system quickly. A craft that performs a powerful burn at a very close perihelion can be placed onto a trajectory with much higher outward speed than would otherwise be possible with the same propellant mass. This can shorten the time to reach the outer planets and can raise the speed of a craft entering the heliosphere boundary region. In a lifetime framing, the method can move the reachable frontier outward for robotic missions and can compress travel time to distant solar system regions. Yet the method still operates within the solar system's energy scale. Gravity assists and close sun burns can raise a craft's speed by factors that matter within planetary distances, but they do not raise it into the regime where light years become lifetime distances. Even the fastest solar system departures achieved by these techniques remain tiny fractions of the speed of light. This means that, while such maneuvers can bring a probe into interstellar space beyond the heliosphere within a human lifetime, they do not bring a probe to another star within that time. The difference is not a matter of better trajectory design alone. It is a matter of orders of magnitude in required speed. Within the solar system, however, these techniques define a practical outer reach. A well-designed robotic mission can use gravity assist to reach Jupiter quickly, to use Jupiter to gain speed, and then to continue outward toward the Kuiper Belt and beyond. It can use inner planet assist to shape a path toward the Sun, and then use a close sunburn to leave with higher outward energy. It can also use multiple planetary encounters to aim at particular outer targets. These are the methods by which human missions have reached the farthest planets, visited icy worlds, and continued outward on long trajectories. For crewed missions, the implications are more restrained. Gravity assists can reduce propellant needs, but the added time and complexity can be costly for a living crew. A close sun maneuver exposes a craft to extreme heat that would require heavy shielding, and heavy shielding raises mass and complicates life support. These factors do not forbid such trajectories, but they make them less attractive compared with more direct paths for nearer destinations such as Mars. The techniques, therefore, tend to remain tools of robotic exploration and of cargo transport, while crewed travel remains closer to direct transfers in the inner solar system. In the lifetime perspective, these methods show that the solar system contains its own internal energy resources. Planets carry orbital energy. The Sun provides a deep gravitational well. A spacecraft can tap these resources through geometry and timing. This can extend reach significantly within the solar system, and can push robotic explorers toward the heliosphere boundary and beyond within decades. It can also raise the achievable outward speed without demanding impossible propellant mass. Yet the methods still leave the craft operating in the same basic regime of tens of kilometers per second, not thousands. They enlarge the lifetime horizon within the solar system, and they clarify why a different class of propulsion would be required to make interstellar destinations truly accessible within a single human life. With these trajectory tools established, the inward path continues toward the solar system's outer boundary itself. The next region is the space beyond the giant planets, the Kuiper Belt, the distant small body populations, and the heliosphere's edge, where the solar wind yields to the interstellar medium. In that region, a lifetime traveler's reach can be described in concrete distances and in decades, and the meaning of leaving the solar system becomes a practical threshold rather than an abstract idea. Beyond the inner planets, the solar system opens into long distances and low sunlight. The giant planets circle far from the sun, separated by wide gaps of space. Beyond them lie belts and clouds of small icy bodies, remnants of formation that trace the edges of the system's early construction. Beyond those bodies lies a boundary defined not by gravity, which reaches indefinitely, but by the sun's outflow of charged particles, the solar wind. For a lifetime in space, this outer region is where the idea of how far one can go becomes concrete. It is the realm that can be reached in decades by the fastest robotic travelers, and it is also the realm where crewed travel becomes extremely demanding in mass, shielding, and reliability. The first outer landmarks are the orbits of Jupiter and Saturn. Jupiter is the largest planet in the solar system, and its gravity shapes the architecture of outer space. Its magnetosphere is immense, filled with energetic particles trapped by magnetic fields. Saturn lies farther out, with a broad system of rings and many moons. Robotic missions reach these planets in years. Their travel times fit comfortably inside a human lifetime, and their exploration phases can last years more. This shows that one lifetime can include a large portion of outer planet exploration, at least in robotic form, and that the solar system is not only a near-Earth domain, it is a reachable family of worlds if time and engineering are available. Farther out lie Uranus and Neptune, and beyond them a transition into a new kind of region. Uranus and Neptune are ice giants, smaller than Jupiter and Saturn but still massive, with cold atmospheres and complex moon systems. Neptune's orbit marks the outer boundary of the main planetary region in the simplest sense. Beyond Neptune, stable planetary orbits continue to exist in principle, but the solar system's known planets end. The region beyond is dominated by small bodies. The Kuiper Belt is a broad zone beyond Neptune, populated by icy objects and dwarf planets. It is not a dense ring, it is a vast volume where objects are spread far apart. Many are small and dark. Some, like Pluto, are large enough to have complex geology and thin atmospheres that change with seasons. The Kuiper Belt is significant in the lifetime frame because robotic missions have reached it within about a decade and can continue beyond it. This means that the Kuiper Belt is not only a theoretical outer zone, it is a visited region, though only by a few craft, and it is within the reach of one human generation's planning and patience. Beyond the Kuiper Belt lies a more diffuse region of scattered objects with elongated orbits. These bodies have been influenced by gravitational interactions with Neptune and the other giant planets. Their orbits can carry them far from the Sun at their most distant points, and then bring them back nearer again. They represent a transition between the stable belt population and the more distant reservoirs inferred from comet behavior. The scattered objects show that the solar system is not a sharply bounded system. It fades into distance through increasingly weakly bound populations. The sunlight in these regions is dim. Solar panels produce much less power, and thermal conditions are cold. A spacecraft traveling there must rely on long-lived power systems or extremely large solar arrays. Communication becomes more difficult because radio signals spread out and weaken with distance. Spacecraft can still communicate, but data rates fall, and transmission can require careful antenna pointing and long listening sessions at Earth-based receivers. The farther a craft goes, the more it must manage its own power, its own orientation, and its own fault recovery. The outer solar system is therefore not only a distance challenge, it is a systems endurance challenge. Beyond the realm of small bodies lies the heliosphere. The Sun emits a continuous solar wind, a flow of charged particles that expands outward and carries the Sun's magnetic field. This wind pushes against the surrounding interstellar medium, where the outward pressure of the solar wind balances the pressure of the interstellar medium. A boundary forms. Inside this boundary, the solar wind dominates. Outside it, the interstellar medium dominates. The heliosphere is not a perfect sphere. It is shaped by the direction of the sun's motion through the galaxy, and by variations in the local interstellar environment. Its boundary regions include complex layers where the solar wind slows, becomes turbulent, and interacts with incoming interstellar particles. The heliosphere boundary matters because it is a physical threshold that can be reached in a lifetime by the fastest human-made spacecraft. A craft that travels outward for decades can reach the outer heliosphere and, eventually, pass beyond the main solar wind influence into interstellar space. This does not mean it leaves the sun's gravity. Gravity continues to bind objects far beyond. It means that the plasma environment changes from solar-dominated to interstellar-dominated. It is a boundary of wind and magnetic influence, not a boundary of ownership in the gravitational sense. The lifetime reach into this region is therefore a reach into the first interstellar conditions. Beyond the heliosphere boundary, a spacecraft enters a medium that reflects the general environment between stars, thin gas, dust, and the galactic magnetic field. It still remains far from any other star. It still travels through a mostly empty volume, yet it experiences a new regime of particles and fields. This is the practical meaning of stepping outside the solar system in a physical sense. It is not a line painted in space. It is a gradual transition into a different background. For a crewed mission, this outer region poses extreme challenges. Travel times to the Kuiper belt are long, often years. Travel times to the heliosphere boundary are longer, often decades with present speeds. A crewed habitat would need to remain stable for that entire period, with no resupply, no repair from Earth, and high radiation exposure. Microgravity effects would accumulate unless artificial gravity is provided. Artificial gravity requires large structures and rotation. Large structures increase mass and area, which increase shielding needs and impact exposure. Radiation shielding would need to be substantial, adding mass and complexity. The requirements do not violate physics, but they push the design toward a generational ship or toward a level of space infrastructure far beyond current capability. For this reason, the outer solar system is best understood as a realistic lifetime frontier for robotic travel, and as an aspirational and difficult frontier for crewed travel. For robotic travel, the region is a domain of quiet extension. A probe can be designed to operate for decades. It can carry a long-lived power source. It can manage itself through autonomy. It can endure the cold and the dark. It can travel outward steadily and send back a slow stream of measurements. Within one human lifetime, such a probe can reach beyond the planets, beyond the Kuiper belt, and into the heliosphere's outer boundary region. This is already demonstrated in the broad sense. The probe becomes a lifetime traveler in a symbolic way. It leaves while one generation watches, and it continues while the generation ages. The outer solar system also reframes the idea of distance. From Earth, the planets are points in the sky. From within the solar system, distances become multi-year trajectories. In the Kuiper belt, a planet is far behind. In the heliosphere boundary region, the sun itself becomes a bright star in a dark sky rather than an all-dominant presence. The star still provides light, but the light is weak. The spacecraft is in a region where space feels more like interstellar space in its emptiness and thin medium. This shift is part of what a lifetime in space can realistically attain today, the experience of crossing from a planet-centered view to a star-centered view and then to a near-interstellar view. The next inward step narrows further by anchoring this region to a specific, well-known benchmark: the Voyager missions and their outward paths. Their trajectories provide a concrete measure of how far a human lifetime can reach with present-day technology in robotic form. They also clarify what it means to leave the solar system, how far one can go in decades, and how slowly light years accumulate at current speeds. Within that benchmark, the lifetime horizon becomes an actual number in distance rather than a general description, and the boundary between solar system travel and interstellar travel becomes a measurable threshold. The Voyager spacecraft provide a quiet benchmark for the farthest reach of human-made travelers within a human lifetime. They are not the fastest possible objects that could be launched from Earth, but they are among the most enduring and among the most distant craft that continue to return data after decades. Their journeys show what present-day technology can accomplish when it is built for long operation and when its trajectory uses the geometry of the solar system to gain speed. They also show, with calm clarity, how slowly distance accumulates when measured in light years rather than in planetary units. The Voyagers begin as missions to the outer planets. Their trajectories are shaped by a rare and favourable alignment that allows a sequence of gravity assists. These assists allow the spacecraft to visit multiple giant planets without carrying the fuel that would otherwise be required to change direction and speed so dramatically. After their planetary encounters, the spacecraft continue outward on hyperbolic trajectories relative to the Sun, meaning they're not bound to return on closed orbits. They coast outward, their speed set primarily by the energy of their departure and the gains from gravity assists. Their outward motion is steady and quiet. Their power supply is crucial to their longevity. Far from the Sun, solar panels would not provide enough power. The Voyagers rely on radioisotope power systems, which convert heat from radioactive decay into electricity. These systems provide modest power that declines slowly over time. This power supports communications, onboard computers, and instruments. Because power is limited, instruments are managed carefully, and some are turned off as energy becomes scarce. This highlights a general truth of deep space travel. Distance does not only challenge propulsion, it challenges power, communication, and long-term system health. As the Voyagers travel outward, they pass through regions where the solar wind changes character. The solar wind is not constant, it varies with solar activity, and it interacts with interstellar space. The transition region is complex. A key concept is the heliosphere, the bubble dominated by the solar wind. The heliosphere has an outer boundary where the solar wind's influence yields to the interstellar medium. Crossing this boundary means the spacecraft enters a region where the particle environment and magnetic field reflect the galaxy's local conditions more than the Sun's outflow. The point of crossing is not a physical wall. It is a gradual passage through changing plasma and magnetic fields. Observations from the Voyagers indicate changes consistent with leaving the solar wind-dominated region and entering the interstellar medium. This provides a practical meaning to leaving the solar system in a physical environmental sense. The spacecraft remains under the Sun's gravity, still travelling outward from the Sun, but its surrounding particle environment becomes interstellar. The craft moves into the same general kind of medium that fills the space between stars. In a lifetime framing, the Voyagers show that decades are enough to reach this threshold. A person can be born, grow into adulthood, and live into later life while a probe launched early in that span travels from the inner solar system to the edge of the heliosphere and beyond. This is a profound extension of reach in the robotic sense. It is still modest compared with interstellar distances to other stars. It is a reach into near interstellar conditions, not a reach to another stellar system. The Voyagers also show the slow conversion of distance into light years at present speeds. Even after decades, their distance from the Sun is still a small fraction of a light year. Light travels vastly faster. A radio signal from Earth reaches the Voyagers in hours rather than years, even at their great distances, because the solar system is measured in light hours and light days rather than in light years. This is why the Voyagers remain controllable by commands and why their data can still be returned. The communications delay is not trivial, but it is manageable. This delay also marks a boundary. Within the solar system, even far out, signals still travel in hours. Beyond the solar system toward other stars, signals travel in years. The Voyagers stand near the edge of this change. Their trajectories also show how direction matters. The Voyagers head outward in different directions, moving through different regions of the heliosphere and into different local interstellar conditions. The interstellar medium is not uniform, so their measurements are not identical. One may encounter different plasma densities and magnetic field orientations than the other. This emphasizes a subtle point. The boundary of the heliosphere is not the same in every direction. It is shaped by the sun's motion through the galaxy and by the surrounding medium. A lifetime traveler aiming outward does not meet one fixed edge. It meets a boundary that varies with direction and with solar activity. In the human imagination, leaving the solar system can be pictured as crossing the orbit of the last planet and then departing into emptiness. The Voyager benchmark corrects this picture gently. The orbit of Neptune is not the end of the solar system's influence. It is the end of the main planetary system. The heliosphere extends much farther. Beyond it lies a medium that is still part of the galaxy. The sun's gravity continues farther still, binding distant bodies on long orbits. There is no single moment when the sun's influence stops. There are only diminishing domains, planets, small body belts, heliosphere, and then the wider interstellar medium. For a lifetime question, the key outcome is that the Voyager-style path represents the realistic farthest reach of present technology within decades. It reaches beyond the planets and into interstellar space in the environmental sense. It does not reach another star. The nearest stars remain several light-years away. A craft at Voyager-like speed would require tens of thousands of years to reach them. This is the simplest statement of the gap. One lifetime can send a machine into interstellar space. One lifetime cannot send a machine to another star with current speeds. The Voyager benchmark also shows the importance of survival over time. A craft travelling for decades must withstand radiation, thermal cycles, micrometeoroid impacts, and component aging. The Voyagers succeed because they are built with redundancy, careful design, and conservative operation. Even so, their instruments degrade and their power declines. In the long term, they will fall silent. This highlights the difference between decades and centuries. A lifetime journey to the heliosphere boundary is possible with careful design. A journey lasting thousands of years to reach another star would require reliability far beyond what has been demonstrated. The lifetime horizon, therefore, is not only a question of distance. It is a question of how long a system can function without repair. The Voyagers also provide a quiet emotional lesson without exaggeration. They show that the solar system, though vast, is still close enough for signals to cross in hours. They show that interstellar space begins not at a planet's orbit, but at a boundary of plasma and magnetic influence. They show that travel across the first fraction of a light year takes decades, and that travel to the nearest stars remains far beyond one human life at present speeds. They are a measurement of reach, a yardstick placed in the darkness. In the inward path, the next layer turns from the machine to the human body. A lifetime in space is limited not only by distance and propulsion, but by biology, radiation, microgravity, and life support requirements set strict constraints on how long a person can remain healthy far from Earth. These constraints define practical crewed reach even within the solar system. They also explain why robotic reach extends farther than human reach in the present era. The next section therefore moves from the Voyager frontier to the limits of human physiology and support systems, staying within the lifetime frame and within scientifically grounded understanding. A human lifetime in space is constrained by biology as much as by propulsion. A spacecraft can coast outward for decades with modest power and careful engineering. A human body requires a stable internal environment every hour of every day. It needs air, water, food, pressure, temperature control, protection from radiation, and a way to maintain health in low gravity. On Earth, these conditions are provided freely by the planet's atmosphere, oceans, and gravity. In deep space, they must be built and maintained artificially. This changes the meaning of distance. The farther the traveler goes, the less support can be provided from Earth, and the more the spacecraft must become a complete life-supporting world. Radiation is one of the most persistent constraints. Outside Earth's thick atmosphere and magnetic shielding, the body is exposed to energetic particles from the Sun and from the galaxy. Solar particle events can deliver high doses over short time. Galactic cosmic rays deliver a steady background of high-energy particles that can penetrate shielding and damage cells. The health risk is cumulative. It increases with time spent in space. A lifetime traveler would face decades of exposure if the mission is long. Shielding can reduce exposure, but shielding adds mass, water, food, and structural materials can provide some shielding. Yet full protection against high-energy cosmic rays would require heavy shielding that quickly becomes impractical for a spacecraft meant to accelerate and travel far. This creates a trade. Distance often demands travel time, and travel time increases radiation exposure, while the protection that reduces exposure increases mass and reduces achievable speed. Microgravity is another constraint. In weightlessness, the body loses bone density and muscle strength without continuous countermeasures. The heart and blood vessels adapt to new fluid distributions. Vision and balance can be affected. Exercise can reduce some effects, but it does not eliminate them entirely over long duration. Artificial gravity created by rotation is a potential solution. A rotating habitat can produce a steady inward acceleration that mimics gravity. Yet a habitat large enough to provide comfortable rotation without severe motion sickness requires substantial size. Size increases mass. Size increases the area exposed to micrometeoroids and dust. Size also complicates shielding because a larger volume must be protected. Artificial gravity can improve health prospects for long missions, but it imposes engineering burdens that push a mission toward larger ships and therefore towards slower acceleration and greater propellant or power needs. Life support is a constant demand. Air must be recycled, carbon dioxide must be removed, oxygen must be supplied or generated, water must be recycled and kept free of contaminants. Food must be stored or produced. Waste must be managed. These systems must operate reliably with redundancy. They must tolerate failures and be repairable with tools and parts carried aboard. In low Earth orbit, resupply and emergency return provide a safety net. In deep space, the craft must survive without that net. Reliability becomes a life-or-death property rather than an engineering preference. Closed-loop life support becomes essential for long missions. A closed-loop system recycles water and air and reduces dependence on stored consumables. Fully closed food production is harder because growing food requires light, nutrients, and controlled environments. It also requires long-term biological stability, microbial contamination, plant disease, and system imbalance can threaten production. A mission that aims to keep humans alive for decades would likely need a combination of stored food and some form of production, or it would need very efficient recycling with large stores. Each option increases mass and volume. Each option increases complexity. Complexity increases the chance of failure unless it is matched by careful design and maintenance capability. Psychological and social constraints also matter. Long isolation, confined spaces, delayed communication, and the absence of natural environments affect mood, cognition, and group dynamics. A crewed mission to Mars already faces these issues at a moderate scale. A mission lasting decades would face them more severely. The craft would need spaces that support mental health, routines that maintain stability, and social structures that handle conflict. These are not speculative concerns. They are grounded in the known effects of isolation and confinement on humans. The lifetime horizon is therefore not only about surviving physically, but about sustaining a functioning community. Medical limitations add another boundary. In deep space, access to full medical facilities is impossible. The crew must carry limited equipment and limited pharmaceuticals. Some drugs degrade over time, and medical procedures are harder in microgravity. A long mission increases the probability of injury, illness, and unexpected health events. As duration increases, the risk grows that something will occur that cannot be managed aboard. This risk can be reduced through crew selection, training, redundancy, and advanced medical systems, but it cannot be eliminated. For a lifetime journey, the probability of needing significant medical intervention becomes non-trivial. These biological constraints define a practical envelope for crewed travel. Within the inner solar system, travel times are measured in days to months. This makes it possible to imagine crewed missions where radiation exposure is limited and where supplies can be carried with margins. The Moon is close enough for rapid return. Mars is far enough that return is not immediate. But the times are still within a year-scale mission. Beyond Mars, travel times grow. Reaching Jupiter would take years. Reaching Saturn would take longer. Even if propulsion could shorten these times, the radiation environment beyond Earth becomes harsher, and the need for long-term reliability increases. The outer solar system therefore pushes crewed travel toward missions that resemble small closed worlds rather than expeditions. For a lifetime in space, a key distinction emerges between reaching a place and living long enough to be there. A robotic probe can reach the outer planets and operate for years. A human crew can reach the Moon and potentially Mars. But the farther outward the target, the more the mission becomes dominated by life support and health. A crewed mission to the outer solar system is not forbidden by physics. It is constrained by mass, radiation protection, and the need for a stable habitat over many years. Within one lifetime, it might be possible only if travel time is shortened substantially, or if habitat technology becomes extremely robust. Both requirements push beyond current demonstrated capability. Maintenance is another quiet limiter. Every mechanical system wears. Filters clog, pumps fail, valves leak, electronics degrade under radiation. A long-duration habitat must be designed for repair. It must carry spare parts or the ability to manufacture replacements. It must carry tools and materials. It must carry knowledge and training. Repair itself requires time and energy. It also requires stable environmental conditions while repair occurs. This pushes the craft toward redundancy, multiple systems capable of taking over while one is repaired. Redundancy increases mass and complexity, which again affects propulsion and reachable distance. The lifetime framing also reveals a difference between traveling far and traveling fast. Traveling fast can reduce time in transit and therefore reduce radiation exposure and reduce the duration over which life support must function without failure. Yet traveling fast demands high energy and often increases exposure to impact hazards because dust and gas collisions become more energetic. Shielding against impacts at high speed adds mass, and that mass increases energy demand. For a crewed craft, the combined requirement of radiation shielding, impact protection, and life support makes very high speed extremely difficult. The biological constraints therefore tend to push crewed travel toward moderate speeds and manageable durations within the solar system, rather than toward extreme speed interstellar attempts. In calm terms, the body defines the inner boundary of reach. A spacecraft can, in principle, travel as long as its power holds and its systems survive. A human crew requires continuous stability, and that stability becomes harder to provide as distance increases and as time extends. The lifetime horizon for crewed travel therefore lies well inside the horizon for robotic travel, at least with current and near-term technology. The most realistic crewed destinations within one life remain the Moon and Mars, and possibly nearer asteroids and orbital habitats. The outer planets and the heliosphere frontier remain better suited to robotic explorers in the current era. With biology defined as a set of constraints, the next inward step turns to a concept that alters how time is experienced at high speed. Relativity allows time dilation for a fast traveler, reducing experienced time compared with the outside universe. This effect could, in principle, extend how far a person could go within one experienced lifetime if speeds near the speed of light were attainable. The next section enters this physics carefully, showing what time dilation can and cannot do for the lifetime horizon without stepping into speculation beyond known science. At very high speed, time does not pass in the same way for all observers. Relativity describes this through time dilation, the slowing of a moving clock compared with a clock at rest in a chosen reference frame. The effect is small at ordinary spacecraft speeds, and becomes significant only when speed approaches a large fraction of the speed of light. Within the title, One Lifetime in Space. How far could you go? Time dilation appears as a possible way to stretch the experienced reach of a traveler. It does not allow faster-than-light travel, and it does not allow signals to outrun light. It changes the amount of time that passes for the traveler, while the outside universe continues to measure a longer interval. Proper time is the time measured by a clock that travels with the traveler. Coordinate time is the time measured in the departure frame, such as the time that passes on Earth, when a craft moves very fast. Proper time along the craft's path becomes less than coordinate time of the same journey. This means that the traveller experiences fewer years than those who remain behind. The effect has been measured on smaller scales, including with accurate clocks flown on aircraft and with fast-moving particles that survive longer in laboratory frames than they would at rest. These measurements support time dilation as a real physical effect, not a metaphor. Time dilation is paired with length contraction. In the traveller's frame, distances along the direction of the motion appear shorter. This is not an illusion. It follows from the same space-time structure that keeps the speed of light constant for all inertial observers. If a traveller moves near light speed, the distance to a far destination is reduced in the traveller's frame, making it possible to cross that distance in less proper time. For the traveller, the universe in the direction of travel is compressed. For the rest frame, the distance remains the same, and the travel time remains longer. Both descriptions are consistent because they belong to different frames. In a lifetime framing, the effect becomes relevant only when the craft can sustain extreme speed. At 1/10 of the speed of light, time dilation is modest. The traveller's experienced time is only slightly less than Earth time. At higher fractions, the effect increases. Near the speed of light, it becomes dramatic. Yet reaching these speeds requires enormous energy and introduces severe engineering challenges, including shielding against dust and radiation. Time dilation therefore comes with a cost that is not optional. It cannot be separated from the propulsion and protection needed to operate in that regime. Time dilation also does not solve the problem of communication. Signals still move at the speed of light, even if a traveller experiences a shorter interval. Messages to and from Earth are still delayed by the light travel time that Earth measures. In the departure frame, a craft travelling to a star several light years away cannot send news back sooner than several years, because the signal must cross the distance at light speed. A traveller might arrive quickly in proper time, but Earth will still wait years for the first signal to arrive, and even longer for a reply to be received. This means that time dilation changes the personal experience of the traveller, but does not allow the traveller to stay connected to Earth in a real-time way. Time dilation also depends on the travel profile. A craft that accelerates to high speed and then coasts experiences one pattern of proper time. A craft that accelerates for long periods and decelerates for arrival experiences another. For time dilation to substantially reduce proper time, the craft must spend a significant portion of the journey at high speed. Brief high-speed segments do not create large reductions in experienced time. This again ties the effect to the practical ability to reach and sustain extreme speed. For a human lifetime, this creates two distinct ways to define the word lifetime. One is the proper time experienced by the traveller, the other is the coordinate time that passes on Earth and in the rest of the solar system. A traveller could, in principle, experience a lifetime-length journey while much longer time passes on Earth. If the traveller moves near light speed for long periods, this concept is physically allowed in relativity. It is also deeply constrained by energy and engineering. A crewed craft would need to protect its passengers from the interstellar medium at high speed. At relativistic speeds, even small dust grains carry large kinetic energy. Impacts become dangerous. Shielding becomes heavy. Heavy shielding increases mass. Increased mass increases the energy required for acceleration. The loop becomes severe. The result is that time dilation can extend the traveller's reach in principle, but it demands extraordinary capability. Within the solar system, time dilation is essentially irrelevant for travel planning. Speeds are too low, and time intervals are too short. The lifetime horizon within the solar system is governed by propulsion, life support, and mission architecture, not by relativistic effects. Time dilation becomes part of the story only when thinking about reaching the nearest stars within an experienced lifetime. Even then, the physics offers no shortcut for those left behind. The journey remains long in Earth time. This distinction matters for the calm conclusion of a lifetime horizon. If lifetime is defined as experienced time, then relativity allows the possibility that a traveller could cross distances of many light years while aging only decades. If the craft could reach extremely high speed, if lifetime is defined as Earth time, then the maximum distance reachable within decades remains limited by achievable average speed, and the speed required for multiple light years becomes extreme. In either definition, the speed of light remains the ultimate bound. The traveller cannot arrive sooner than light in Earth's frame, and the traveller cannot send information faster than light. The effect also highlights a quiet human truth. Even if near light speed travel were possible, it would separate the traveller's life from the life of those who remain. A traveller could return having aged little while decades or centuries pass on Earth. This is not a dramatic statement. It is a direct consequence of time dilation. It would change the social meaning of a lifetime journey. It would also change the meaning of home. Yet this lies outside the core physical question of reach, and the physical question remains bound by energy and survivability. For the purposes of a realistic documentary tone, time dilation is best treated as a known physical effect that does not currently extend human reach, because present spacecraft speeds are far too low. It provides an upper boundary on what is physically possible without breaking known laws. It also clarifies that the interstellar distance problem is not solved by clever thinking about time. It is solved only by achieving high speeds, and high speeds require energy and protection. With relativity placed in its proper role, the inward path can now return to propulsion in a cautious near-future sense. The next step considers concepts often discussed in scientific and engineering literature, such as fusion propulsion and beamed sails. These concepts aim to raise speed far beyond current spacecraft, potentially bringing interstellar distances into the range of decades. Their feasibility remains uncertain in engineering practice, and the discussion will state what is known and what remains uncertain without speculation, keeping the lifetime horizon grounded. To go farther within one lifetime, a spacecraft must be faster than any that has yet traveled through deep space. This requires propulsion and infrastructure beyond what is currently demonstrated. Several concepts are discussed in scientific and engineering contexts because they remain compatible with known physics and because they address the main obstacle, which is speed. These concepts do not promise that interstellar travel is near. They show how the problem might be approached if energy, materials, and engineering maturity advance substantially. In a calm and grounded view, they represent plausible directions, each with clear constraints and major uncertainties. Fusion propulsion is one of the most often discussed paths because fusion reactions release far more energy per unit mass than chemical reactions. Fusion combines light nuclei into heavier ones, releasing energy and producing energetic particles. In principle, a fusion-powered rocket could achieve much higher exhaust speeds than chemical rockets. Higher exhaust speed means higher efficiency in converting propellant mass into change in velocity. This could reduce the mass ratio problem that makes chemical rockets unsuitable for very high speeds. It could also allow a craft to accelerate for longer periods and reach higher cruise speeds, potentially shrinking travel times to the outer solar system and, in more ambitious concepts, to interstellar distances. The uncertainty is practical control. Sustained controlled fusion for power and propulsion in space remains unproven at the scale required. A fusion engine must confine very hot plasma, manage radiation and particle flows, and reject waste heat. It must operate reliably for long durations without extensive maintenance. It must also carry fuel that can be stored safely for the mission duration. Different fusion fuel cycles offer different advantages and difficulties. Some are easier to ignite in theory but require rare fuels. Others use more abundant fuels but demand more extreme conditions. These are real engineering trade-offs that remain unresolved. Observations indicate fusion powers the stars naturally, but engineered fusion for propulsion is a separate challenge. Even if fusion propulsion becomes practical, its role in a lifetime journey depends on mission type. A fusion craft that aims to reach the nearest stars within decades would likely need to reach a significant fraction of the speed of light. That would demand enormous energy and would intensify hazards from dust and radiation. A fusion craft that aims for more modest speeds could still be transformative within the solar system, allowing faster trips to the outer planets and shorter cargo cycles. In this sense, fusion may extend the lifetime horizon outward within the solar system before it makes interstellar travel realistic for humans. Beamed sails represent a different approach. Instead of carrying all energy on board, a sailcraft is pushed by a powerful beam, such as a laser, emitted from a distant station. The sail reflects the beam's photons, and photon momentum provides thrust. The craft can be very light because it does not carry fuel in the rocket sense. This makes high acceleration possible for small payloads. In principle, a beamed sail could reach high fractions of the speed of light for tiny probes, potentially allowing them to cross the interstellar gap to the nearest stars in decades. The uncertainties here are infrastructure and control. A beam powerful enough to accelerate a sail to high speed requires an immense energy source and a very large phased array or optical system to keep the beam focused over long distance. Diffraction causes beams to spread, so a tight beam at long range requires a large aperture and precise alignment. The sail must remain stable within the beam, resisting tilt and drift. It must also survive heating. Even a highly reflective sail absorbs some energy. At high beam intensities, that absorbed energy can damage or destroy the sail unless heat is radiated away effectively. Materials that can survive this environment must be extremely light, strong, and thermally stable. These requirements remain difficult. Beamed sails also face the problem of stopping. A sail accelerated from Earth's region would coast toward its target at high speed. Unless it has a way to brake, it would perform a fast flyby, gathering data in a brief window. Braking might be possible through interaction with the target star's light or stellar wind, but the effectiveness depends on sail size, approach geometry, and the local plasma environment. Full braking to enter orbit around another star appears far more difficult than simply reaching it. This suggests that the earliest feasible interstellar sail missions, if they occur, are likely to be robotic flybys rather than crewed arrivals. Another concept is staged infrastructure within the solar system. Even without interstellar travel, building refueling depots, power stations, and manufacturing capabilities away from Earth could extend how far a lifetime traveler can go within the solar system. Nuclear power systems, in-space resource use, and reusable transport architectures could reduce the cost and risk of reaching Mars and the outer system. A lifetime traveler might go farther not because propulsion becomes exotic, but because the supporting network becomes stronger. This is a quieter kind of progress. It turns space travel from isolated expeditions into a system with supply lines and repair capabilities. For interstellar reach within a lifetime, the most physically plausible candidates remain small robotic probes rather than human crews. Robotic probes can be made small enough to accelerate with beam propulsion. They can accept higher radiation doses. They can accept higher risk of dust impacts. They can operate autonomously. Their data can be returned slowly over years without requiring a living habitat. A human traveler cannot accept the same constraints. A crewed craft must be large enough to protect and sustain people, and that mass increases energy requirements sharply. It also increases the challenge of accelerating to near-relativistic speeds. The gap between robotic feasibility and crewed feasibility remains large in the near-future conceptual space. Uncertainties remain without needing speculation. It is uncertain whether a fusion propulsion system suitable for spaceflight will be developed in a form that is efficient, reliable, and light enough for major speed increases. It is uncertain whether beam sail infrastructure will be built at the scale needed for interstellar probes, though it remains within known physics. It is uncertain whether materials and control systems can provide stable sail flight under intense beams. It is uncertain how the interstellar medium's dust distribution would affect extremely fast sailcraft over several light years. Observations indicate interstellar dust exists and that it becomes dangerous at high speed, but the detailed risk profile for a specific mission remains uncertain. In a lifetime context, these concepts shift the horizon but do not eliminate the core constraints. The speed of light remains the limit. Energy cost rises steeply with speed. Shielding becomes heavier as speed rises. Reliability becomes harder as travel time rises. A concept that reduces travel time must manage higher impact energy. A concept that reduces impact energy by slowing down must manage longer exposure and longer system endurance. The trade persists. What these concepts do provide is a path to the final inward framing. They allow a clear comparison between destinations that are achievable within a lifetime with current technology, destinations that might become achievable with expanded solar system infrastructure, and destinations that remain out of reach without an enormous leap to relativistic travel. The next section narrows the question to explicit targets and scenarios: the Moon, Mars, the outer planets, the Kuiper Belt, the heliosphere boundary, and the nearest interstellar space. Each will be considered in a lifetime budget, showing what fits and what does not under different levels of capability, without stepping outside what is physically grounded. Within one lifetime, the reachable targets depend on whether the traveller is human or robotic and on what level of propulsion and infrastructure is assumed. The targets also depend on what it means to go. A flyby differs from a landing. A short visit differs from long residence. Yet even with these variations, the solar system provides a clear ladder of destinations that can be placed on a lifetime scale. Beyond the solar system, the nearest interstellar distances remain a different regime, approachable in decades only under propulsion concepts far beyond current practice. This section places the main targets into that ladder, from the most accessible to the most distant, keeping the focus on what fits within a life. The Moon sits as the nearest major destination. It is close enough that travel time is days, not months. It is close enough that communication delay is seconds. It is close enough that emergency return is possible in principle. In a lifetime budget, the Moon can be visited repeatedly. It can host long stays if habitat and logistics are developed. Its harsh environment remains real, with vacuum, radiation, and temperature extremes. Yet its proximity makes it the most practical place for long-term human operations beyond Earth. For a lifetime traveller, the Moon is not a limit. It is a beginning. Near-Earth asteroids and other small bodies in accessible orbits form a next category. Their distances vary, but some can be reached on trajectories comparable to lunar or Mars missions. They lack atmospheres and have low gravity, presenting new operational challenges, but they also offer potential resources and scientific value. For a lifetime traveller, a small body mission is plausible in terms of time. It is constrained by navigation, mission planning, and life support rather than by basic travel duration. Small body visits can also serve as training grounds for deep space operations, because they require living away from Earth's immediate safety net. Mars is the next major step. Its travel time is months for typical trajectories and depends on planetary alignment. A round trip with time on the surface can occupy a few years, still within a lifetime. The main constraints are radiation exposure, life support reliability, surface hazards, and the difficulty of launching from Mars for return. In a lifetime framing, Mars is a destination that can be reached and potentially inhabited for part of a life, if the necessary systems are developed. It is far enough to require serious autonomy and robust engineering, yet near enough that a human mission is not prohibited by time alone. The asteroid belt is another reachable region. It lies between Mars and Jupiter and contains many small bodies. Reaching the belt is possible within years. The challenge becomes the need for supplies, radiation protection, and the ability to operate far from Earth. For robotic missions, the belt is routine. For human travel, it would require advanced logistics and reliable habitats. Within a lifetime, it is possible in principle to travel to selected asteroids and return, but such missions would be ambitious and would likely follow the development of deep space infrastructure. Jupiter and Saturn lie farther out. Robotic missions reach them in years. A human mission would take longer and would need to handle deep space radiation and long isolation. Jupiter's radiation belts are especially intense, creating a hazardous environment for unshielded humans and sensitive electronics. A crewed mission could in principle avoid the worst regions by choosing trajectories and orbits carefully, but the challenge remains. Saturn is less intense in radiation than Jupiter, but still far and cold. In a lifetime budget, reaching Jupiter and Saturn with a crew is not impossible in the pure sense of travel time, but it becomes extremely demanding in life support and shielding. The question becomes not whether the journey fits within decades, but whether the craft can sustain a crew safely and reliably for the years required and then return. Uranus and Neptune push farther. Robotic flybys occur on long timescales measured in many years. A crewed mission to these distances would likely require travel durations that, while still within a lifetime, are long enough to make every biological constraint heavier. Radiation exposure accumulates. Supplies must be stored or produced. Repair capability must be robust. Communication delay becomes many hours. The practical result is that these planets are more plausible targets for robotic exploration within a lifetime than for human visitation. A human might see them through instruments and data within a lifetime. Direct travel would require a level of deep space habitation beyond current practice. Beyond Neptune, Kuiper Belt objects become the next ladder rung. Robotic missions can reach selected objects within a decade or two, depending on trajectory and propulsion. A lifetime is long enough for such missions to be planned, launched, and completed in the sense of arriving and returning data. For a human traveler, reaching the Kuiper Belt within a lifetime is a more extreme undertaking because the travel time is long and the return is difficult. A mission might be possible only as a one-way journey with settlement-style life support, or as a mission requiring propulsion and logistics beyond what has yet been demonstrated. The heliosphere boundary and nearby interstellar space are the next category. Robotic spacecraft have reached this region over decades. This is a lifetime-scale achievement in the sense that one generation can witness the launch and the crossing. For a human crew, reaching the heliosphere boundary within a lifetime would require living in deep space for decades. This raises the full set of long-duration problems: radiation, microgravity, medical risk, and system longevity. Artificial gravity and heavy shielding would likely be needed. The craft would become a small world, and the mission would resemble an isolated colony more than a voyage. Within a single life, it could be possible in principle if technology supports a durable habitat, but it remains far beyond current human spaceflight practice. Beyond the heliosphere boundary lie the nearest stars, several light-years away. Within current technology, they are unreachable in a lifetime. Even the fastest probes would take thousands of years. Within speculative but physically grounded concepts such as beamed sails for small probes, a near-star flyby might be achieved in decades. For humans, reaching even the nearest star within one lifetime would likely require near-relativistic speeds, implying extreme energy, extreme shielding, and profound engineering challenges. Time dilation could reduce the traveler's experienced time if such speeds were reached, but the outside timeline would still span years, and the ship would still have to survive the interstellar medium at high velocity. The calm conclusion is that the nearest stars remain beyond the lifetime horizon for crewed travel under any technology that resembles current engineering. While they might become reachable for tiny robotic probes if large infrastructure is built, within a lifetime, therefore, the targets fall into three broad practical groups: the inner solar system, including the Moon and Mars, is reachable for humans with plausible future development. The outer solar system and Kuiper belt are reachable for robots, and potentially reachable for humans only with advanced deep space habitation and very robust logistics. The heliosphere boundary and interstellar space are reachable for robots within decades and remain extremely challenging for humans. The nearest stars remain outside the lifetime horizon for humans, and they remain far even for machines unless propulsion advances by orders of magnitude. This placement of targets completes the practical map. It shows how distance, time, propulsion, and biology combine to define reach. It also prepares the final inward step, which is to state the most realistic upper bound for how far a human can go in one lifetime, keeping the tone calm and the facts grounded. That final step will gather the constraints into a single horizon, not as a single number, but as a clear boundary between what fits within a life and what belongs to longer timescales. A single lifetime in space is a question of reach within strict boundaries. The boundaries are not only distance and propulsion, they are time, biology, and the slow loss of reliability in any complex system. When these boundaries are held together, a practical horizon appears. It is a horizon that reaches far beyond what any person can see with the naked eye, yet it remains far short of interstellar destinations. It is a horizon measured in months and years for the inner solar system, and in decades for the farthest robotic travelers. It is a horizon that, for humans, is likely to remain within the solar system for the foreseeable future under known physics and realistic engineering limits. Within the solar system, one lifetime can reach the moon many times. The moon's travel time is short, and its proximity allows support, rescue, and steady logistics. A person could spend months or years there if habitats are built and maintained, and still return to Earth well within a lifetime. The moon is a reachable frontier because distance is small and because communication delay is negligible. It is also a place where space conditions are real and persistent, making it a natural testing ground for longer missions. Within the same lifetime, Mars is reachable. Travel to Mars requires months of transit, careful alignment, and a commitment to living with delayed communication and limited resupply. A mission to Mars and back fits within a few years. The limiting factors are not the calendar alone. They are radiation exposure, life support reliability, and the complexity of surface operations and return. Yet these are engineering and operational challenges, not time barriers. In the lifetime map, Mars stands as the farthest major planet that is clearly within reach for crewed travel in a single life under plausible development. Beyond Mars, the horizon becomes less about time and more about biology and mass. Jupiter and Saturn are reachable by robotic missions in years, and a human lifetime is long enough in principle to travel to them and return if propulsion and life support systems are advanced. The practical limits are severe. Radiation environment, especially near Jupiter, requires heavy shielding or careful avoidance. Long duration requires robust life support, medical capability, and redundancy. The farther the craft goes, the more it must carry everything it needs, because resupply becomes unrealistic. The spacecraft becomes a small artificial world. It must remain stable for years while exposed to radiation and isolation. Within one lifetime, these missions are not prohibited by the clock, but they are constrained by the mass and reliability required to keep a human crew alive and healthy. The outer solar system and the Kuiper belt extend the same challenge. Robotic craft can reach these regions within a decade or two. A human could travel outward for years within a lifetime, but returning or operating meaningfully would demand a habitat capable of sustained life support and protection for a long span. microgravity, radiation, and the risk of medical events accumulate. Artificial gravity can reduce some physiological decline, but it imposes large structural requirements. Shielding can reduce radiation, but it adds mass. Mass increases propulsion demands and reduces achievable speed. These constraints push a crewed mission to the far outer system, into a category closer to a settlement-style project than to an expedition. The farthest reach of one lifetime under present technology is most clearly expressed by robotic travel to the heliosphere boundary and beyond. A probe launched early in a person's life can, in decades, reach the region where the solar wind yields to the interstellar medium. This is a real threshold in the environment, and it is reachable within one human lifespan in the sense that the full journey can occur while a generation is alive to see it. This is the practical maximum of present-day reach for physical travel beyond the planetary system, and it exists primarily for machines rather than for people. In light years, this reach remains small. The heliosphere boundary lies far from the Sun in solar system terms, yet it is still a small fraction of a light year. The nearest stars remain several light years away. Even the fastest existing spacecraft would require tens of thousands of years to reach them. This places interstellar travel to other star systems outside the lifetime horizon with current propulsion. It also places it outside the lifetime horizon for humans under any near-term engineering that resembles present spacecraft in mass and protection. Physics allows a different answer in principle for very small robotic probes. Beamed propulsion concepts suggest that a tiny sailcraft could, in principle, reach a significant fraction of the speed of light, potentially crossing to the nearest stars in decades. This would extend the lifetime horizon for machines into true interstellar travel. The feasibility of such missions depends on large infrastructure, advanced materials, and precise control. It also depends on surviving dust impacts at high speed and on returning data across light-year distances. These constraints remain large and uncertain in practice, yet they remain within known physics. Even if such probes become possible, they do not imply that humans can follow within one lifetime, because crewed travel demands mass and protection that make extreme speeds much harder to achieve. Relativity offers time dilation, which can reduce the time experienced by a traveler at near light speed. This could, in principle, allow a person to experience a long journey while aging less. Yet reaching the speed regime where this matters requires enormous energy and imposes severe hazards from interstellar dust and radiation. It also does not reduce the time that passes in the outside universe. It does not shorten communication delays. In a practical lifetime framing, time dilation is therefore not a tool for current reach. It is an upper boundary that remains distant. The calm practical horizon can be stated plainly. For humans, one lifetime can realistically include extensive travel and living in near-Earth space, repeated lunar missions, and, with future development, a mission to Mars and potentially time on Mars. Beyond Mars, crewed travel within one lifetime becomes increasingly limited by biology, radiation, and the mass of the systems required to sustain life and repair. For machines, one lifetime can reach the outer planets routinely, the Kuiper Belt in a decade-scale mission, and the heliosphere boundary over decades. Beyond that, machines can continue, but the journey becomes longer than a life unless propulsion advances dramatically. The deeper meaning of the horizon is not despair, it is clarity. The universe is large, and one lifetime is short. Technology can extend reach, but it must obey the speed limit of light and the energy costs of acceleration. Biology adds further constraints that do not yield easily. Within these constraints, the solar system remains the natural domain for human travel within one life. It contains many worlds, and its distances are measured in months and years rather than in years of light travel. The nearer stars remain beyond the reach of a single human life under realistic assumptions. They remain visible, measurable, and knowable through observation, even as they remain unreachable by travel within one lifetime. The lifetime horizon therefore settles into a quiet shape. It is wide in the inner solar system and narrow at the edge. It reaches outward to the Moon and Mars in human terms, outward to the outer planets and heliosphere boundary in robotic terms, and outward to the stars only in the form of light and radio waves. The furthest a person can go in one lifetime is likely to be measured not in light years, but in astronomical units, and in years of careful living inside a moving habitat. The answer remains calm because it is an answer about scale. A lifetime is a small span, yet it can still hold a long journey. It can hold years in orbit, months in transit, and time on other worlds. It can hold the building of systems that outlast a single person and carry machines farther than humans can safely follow. It can hold the patience to send explorers into the dark that will continue travelling long after the people who launched them are gone. Space remains quiet and immense. A lifetime remains brief and precious. The distance between these facts defines the horizon, steady and clear.